Okay, so welcome back. This is our fourth video about sampling, and now we're going to discuss a little bit about mixing chains. So as we saw in the previous video, we use this term mix to denote that the chain is close to the stationary distribution pi. So we want to start sampling from the chain only after the chain has mixed, so only after the chain is close enough to the stationary distribution. That is the distribution specified by the Bayesian or the Markov network. However, we need to have a test to know if the chain has mixed or not. And unfortunately, there is no such a test. What we do in practice is to run different tests, and if we find no evidence that we have a non-mixing chain, so we assume that the chain has mixed. So how do we know that the chain has not mixed? What we do is to compare statistics over windows. So we can have only one chain. So imagine exactly how we did in the previous lecture, in the previous video, where we started with one random assignment and starting to change that assignment using the transition probability specified by the Gibbs distribution until we reach the mixed state. So this is only one chain. What we can do, and it's better than that, is start in parallel several of those chains. So we start with several assignments chosen in a certain way and starting changing those assignments in parallel. And we can use statistics over those chains in order to check if the chains had not mixed yet. So the idea is to use some slide windows. So we can have a large chain like the one that is illustrated here, and we can compute statistics over different windows. So we have this window 1 here and the window 2 here, and we can compare if the statistics are similar or not. If the statistics are similar, we may think that the chain has mixed, and maybe it's time to start sampling from this chain. The best thing that we can do is have several of those chains, and we have windows over these different chains, and we compare statistics over the different chains. So one popular method to test for convergence is to compare what we call the within and the between chain variance, right? So what we have here illustrated in this figure are the different chains. So we have the chain 1, the chain 2, the chain 3, until the chain 4. So this is, in my equations here, the index J. Right? And what we have for A here is actually what we have observed in the chain. So we have here the first observation until the observation number n. So when we compute this average here is for one chain J, we're going to take all the values that we measure over this chain, and we're going to compute the average for this. So we apply our function that converts the instantiation into a value 0, 1, and we take the sample mean for this chain, right? So exactly what we are computing here. So we have one sample mean for each chain. So what we can also do is to compute the sample variance. So the sample variance is here. I'm going to jump the second one and come back later. So we have the sample variance here. So basically the equation that we saw before, and we are computing the sample variance for each chain. So it's basically the difference, the distance between the values that we have from the function to the average that we computed in this first step here. So this value here, the sample variance, is going to be 1 for each chain. So we have the average for the first chain, they have the average for the second one, the average for the third one, and so on. And we also have the sample variance for each of those chains. So what we call W here, that is this within chain variance, is simply the average for all the sample variances that we computed for each chain. So what we expect here to happen is the following. We have a very large state space that I'm going to represent here by this square. And this state space, it should have some subspace that we have a very large transition probability between the states that we have here. Right? And we should have as well some really small probabilities that connect to other spaces in the state space that have large transitioning probabilities between them. And we keep on doing this. So we have this space here, we have this space here, we may have another space here that we can transition with high probabilities that have somewhat smaller probabilities that connect to the other states. So if we start here, what's going to happen is that we're going to transition here and keep transition here in the beginning. And if we measure the average here and the variance, the variance tend to be very small around to the average that we have here. So that's what is going on here for the chains 1, 2, 3, and 4 in the beginning. But with time, what's going to happen is that eventually we're gonna sample and change from this space here to this another space here. And with more time, we're going to transition from this space to this other space. So I'm going to start to mix the chain. The chain is going to visit all possible states that we have in the state space. And I'm going to start to approximate the stationary distribution. Note here that this within chain variance should be small and around the average for each of the chains, right? So we can have one average here, one average here, another average here, and another average here, and we have these small values for W. And we can also compute another two things. One is the first here, that is simply an average of the averages. So we are computing the average of the sample means. And as we take this, we can also compute the B. And the B is the sample variance between each sample mean and this average of the sample means. And what we can expect here in an intuitive way, let me just erase this because it's becoming too messy. And also this is that this value here, so this guy here is going to be like one average that we have here, more or less in the middle. And when we compute this, we are actually taking what is the distance between this average and so this is one of the average that we are considering, right? And this average of the average. And we're going to take this for each of the chains and we will compute the sample variance. So we are comparing each one. So this is going to be the 1 and this is going to be the 4, and also we have for the 2 and the 3, and we're computing this. So we can expect that this quantity here, the W, is going to be small, right, in the beginning, and the B is going to be large because we have those chains separated from each other. But as they start to mix, we expect that we have this situation here. We cannot differentiate in between the chains because all the chains have visited the states of our space state, so they are all very well mixed up. So in this case, the W should approximate the B. And that is exactly what is being computed in this equation here. So what we have in the numerator is something that's actually very interesting, right? If we look here, and as W increases, we're going to have a smaller value for this part here. And also we have a smaller value as the number of instances increases. So if we collect a lot of samples, we expect that these samples, these chains, will mix it up. So we have two conditions here. Or we have collected a very large number of samples, or W has approximated B. In these two cases, this ratio R will converge to the number 1, right? Because I'm going to disappear with this part of the expression here, and we will end up with W over W. So we have a rule of thumb here that when this value of R is smaller than 1.1, it tends to start with a very large value, but tends to decrease with time. And when it reaches 1.1, we say that the chains have converged. So this is one technique. It's frequently used. There are no guarantees, but it tends to be a good heuristic. So once the chains have mixed, we start to collect samples to answer the queries. And one frequent question is that should we take every sample, or we should take one sample every 10 iterations? What should we do? So there are papers making different recommendations for this. So there are papers that say that you should wait 100 iterations. Others say that you should take every sample that we generated from the chain. And and there are papers that actually do that. They show that the best estimates come from when we take every instance that we generate from the chain. So there is no need to wait for a certain amount of time to take the instance. But we should be quite carefully because the instances are highly correlated. So if we look at the chain, the difference between two consecutive samples is potentially just one variable, right? And so they are highly correlated. So we cannot use the bounds that we computed in the first part of this lecture because those bounds are for IID samples. We only take one sample every 100 in the cases that we have computational issues, right? So if we have not enough memory to store all the samples, or we don't have enough processing to process all the samples to compute the probabilities, the results for our queries. So in this case, we can sample one every, I don't know, like 100 iterations. So in this case, we will have less samples, and we'll have less correlated samples as well. One interesting observation is that if the chain mixes fast, so the samples tend to be less correlated. But if you have a slow convergence, so it means that the samples will be highly correlated because we are moving slowly into the space state. So slow mixing is an indicative of a problem, right? Because it's going to take long to mix the chains, and you're going to take a large amount of time or large number of samples in order to have a good sample to answer the queries. So this is the algorithm for the MCMC, and this is the first part that they call the burn-in. The second part is the sampling. So we're going to take as input the network N with variables X, induce a probability distribution P with evidence E, and also a number of chains C. So now we're going to simulate more than one chain at a time. And we're going to output some instances that are going to be at least one instance for each chain. So we start with the variable I equals 0, and the variable I will control how many samples we have generated for each chain, exactly as we did in the slide that we were discussing the convergence of chains. And we also have the variable J that will control the different chains. So now I start by iterating over the chains, and I'm going to generate one complete instantiation for each variable that we have in the network. So we do that for all the variables that we have in the network, but we don't need to do that for the evidence variable. So we take the evidence variables out. So that's the best thing that we can do here is to start with a sample that is compatible with the probability of X given E, if that is possible. So even though we can start with random assignments, sometimes random assignments, they take too long for convergence. So something that is very common practice is to do likelihood weighting and take a few samples generated by likelihood weighting with different probabilities. Sometimes people take for some chains states with high probabilities, and for other chains they start with states with low probabilities and so on. So now we go to this part of the algorithm here that we're going to iterate while we have not mixed the chains yet. And this part is very simple, given that we have already discussed this, how the Gibbs sampling works. But we're going to iterate over the chains. We're going to select one variable randomly that is not one evidence variable, and we're going to sample a very little x for this variable according to this distribution here. So this is the transition distribution for the Gibbs chain. Is the probability of x that you are interested given a complete assignment for all variables but x. So we're going to look here. This is the assignments. So these are the values that we already have in the assignment. These are the evidence variables. These are all instantiated, and we have this variable x here. That's the only one that is not instantiated that we need to sample from. So once we get this value little x here, what we have to do is to change for the current chain the value of x in the instantiation that we had before. So this is what this operator here means. And we increase I, and we can check now for convergence. And we can use a criteria such as the R that we discussed in the previous slide. So we keep on doing this, and when we believe that we have converged, so we have a mix of the chains, so we stop and we return. And now here we have several possibilities for doing this, but it's very likely that you be interested in returning at least a window of samples that we use it to check for the convergence, that you know that the chains have converged, so you don't want to lose those last samples. So it's very common to return at least one window of samples for each chain. So this is the sampling algorithm. That is the algorithm that's going to take now the samples and start to collect them to answer the queries. So we have the network N, variables X, distribution P, evidence E, the number of chains C, and also the instance that we returned from the burn-in procedure. So now what we're going to do is to start a data set D empty, and I'm going to start to generate samples. We're going to generate enough samples, so there is not a pre-specified value here, and that's going to be another thing that we need to decide about the design of the algorithm. But here we're going to iterate over the different chains, and for each chain I will do the transitioning according to the Gibbs distribution. So select one variable at random that's not evidence, sample a value little x. I'm going to change the current instantiation by changing the value of the variable x to this little x, and I'm going to put that sample into the data set. I'm going to iterate that and return the data set. Again, there are many ways of doing this, and a common way is, again, to compose this data set by a set of samples that we brought from the burn-in stage that we checked for the convergence, so we are confident that the chain has converged. So we take the samples from the burn-in stage, at least a window of those samples, and we integrate with more samples that we get here from this algorithm. So this is the summary of the Gibbs sampling. So we want to get to the target distribution, that is the one specified by the Bayesian network or the Markov network. So in this case, what we do is a Markov chain with a very large state space. We can think that each complete assignment x from all the variables x is one state in this chain. So it's going to be a huge state space. It's impossible to do what we did before. If you remember that we used the forward algorithm to compute the stationary distribution, that's not possible to do this now, because we can think that we have this huge state space, and if we want to specify this complete transition matrix, it's going to be this large space squared, right? Because we have to specify the probabilities, the transition probabilities for every pair of state. So it's going to be impossible to do this. What we do instead is to specify the transition probabilities for the Gibbs sampling that are going to be much more efficient to compute. And those transition probabilities are actually these ones, right? So they are specified here. So it's this guy here. It's simply the probability of the variable that I want to sample given a complete assignment for all the other variables that we have in the network. Part of them are evidence, another part is not evidence. It just excludes the variable that we are sampling. So one important question is that, is the Gibbs chain irreducible? So it is a regular chain, because if it is a regular chain, so it's guaranteed that it's going to have just one stationary distribution. That's going to be the distribution specified by the base or the Markov network. And the answer is not always, but actually we have a guarantee if the factors are all positive. So in this case, it's guaranteed that the Gibbs chain is going to be regular. So one simple example that we can build to show that the Gibbs chain is not regular is using the XOR. And for instance, let's suppose that we have evidence that y is equal 1. In this case, we can rule out everything that says that y is equal 0. We can also remove these lines here because they have probability 0, so it will not change anything. And we can see that given evidence y equal 1, if for instance we are sampling x1 and we have x2 equal 1, we have just one line that's compatible with this. And in this case, I can only go to x1 equals 0. So I cannot go to the other state x1 equal 1, because in this case here, this guy is not compatible with this one here. And the same thing happens if we specify the value for x1 and try to sample x2. So it's not guaranteed to be a regular chain if we have 0 probabilities. But if the factors are all positive, so the Gibbs chain is irreducible. Alright, so we got to the end of this lecture, and we saw the sampling methods. These are powerful techniques for approximate inference, but again, pretty much like we saw for the belief propagation, they are not easy to use. So when we design a sampling algorithm, we have to take in account very different design decisions that we have to make, and those design decisions may influence the outcome. So we may have some good results when we choose the right parameters. Sometimes we don't. So we have examples of decisions that we have to make, like the number of chains that we're going to use, the size of the windows, what's going to be the mixing criteria, what's going to be the parameters that we're going to compare. We saw that we used a function that was f alpha, but we did not specify what's going to be alpha. Usually alpha are different set of variables that we have in the network. So we need to specify these and many other parameters. So it's a very complicated procedure. It doesn't mean that it doesn't work. Actually, it does, and it's very powerful. If you look today, there are several softwares for statistical Bayesian inference, and most of them, they use sampling as the main inference method. So these are really powerful techniques, but they do require quite a bit of effort to make them work. Okay, so that's all for this week. And in the next week, we're going to discuss learning in Bayesian networks. So see you next week.